Here's another worked example on perfect frames, and this is solved using method of joins. As you can see in the figure, this is a perfect frame with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 members, one end of which is fixed and the other end is a roller support, and you have two loads vertically downward, one at 4 meter from point A, which is of 3 kilonewton, and another at 8 meter from A, which is of 6 kilonewton. Both are acting vertically downwards, and you have an 8 kilonewton load acting parallel to the x-axis and towards the positive axis, positive x-axis, which and that is at 1.5 meter perpendicular distance from the x-axis or point A. So first of all, we need to, for the analysis, we need to find the reactions at A and B. Because you have a horizontal force, you will have a horizontal reaction at A. There is a vertical reaction as well, and you will have both horizontal and vertical reactions at the support A here. So let's take moments about A, and you will have to consider 3 kilonewton, 6 kilonewton, RB, and the 8 kilonewton forces when taking moment about A. So you have 8 that is acting at 1.5, so 8 into 1.5 plus 3 into 4, which is the force here acting at 4 meter from A, plus 6 into 8, which is 4 plus 4, 6 kilonewton, will be equal to the total distance of 12 into RB. About A, the 3 kilonewton will be creating a clockwise moment, 6 kilonewton again clockwise moment, 8 kilonewton again clockwise moment about A, but RB is creating an anti-clockwise moment about A. So only RB will have a different sign, and that's why RB is taken to the other side of the equation. So from this you can calculate RB equal to 6 kilonewton, and vertically making the system into equilibrium, you have 3 plus 6 is equal to RB plus RA vertical. So you have RB equal to 6 and RA plus RB equal to 9. So RA vertical will be 3. And obviously there is only one horizontal force. So you have RA horizontal is equal to 8 kilonewton. So now you have a triangle and all these angles are given theta. So these are all same angle. So you will need to find the hypotenuse of this triangle here. You have the 4 meter distance. The base of all the triangles are given, and you will need to find this side. For that, let's consider a right triangle here, assuming making a right triangle here like this. Yeah, you will have a right triangle like this. So for this triangle, let's call it ACX. From ACX, you have AZ equal to, this is 4 meter, and this will be dividing the AX is half of 4, so that's 2. So AC will be equal to 1.5 square plus 2 square, root of 1.5 square plus 2 square, that's 2.5 meter. And you can calculate sine theta and cos theta from that. Because AC is 2.5, sine theta will be CX divided by AC, which is 1.5 by 2.5 equal to 0.6, and cos theta will be AX divided by AC, which is 2 divided by 2.5, that is 0.8. Now the fundamentals to calculate or to analyze the problem has been completed. Now we can move on to analyze the joins one by one. Let's consider the first join here, that is the joint A. We're moving on to the first joint, and now on the problem is exactly the same as the ones that we did before. So let's see the joint A. On joint A you have AC, the force on this member, the force on this member, and the reaction, vertical reaction at A and the horizontal reaction at A. The only inclined force is FCA here. So if you find the equilibrium in vertical direction, you can see the vertical component of this force should equal the reaction, the vertical reaction at A. So you have the vertical component of this force is FCA sine theta, and that should equal RAV. So RAV equal to FCA sine theta, FCA equal to 5 kilonewton compressive. You can see FCA should act in this direction. Then only you will have a vertically downward component. So this component should be vertically downward so that it should balance RAV. So this is a compressive force. Because that is acting towards the joint, this is a compressive force. Now, the cos component of this force, the horizontal forces in this joint are FFA, the cos component of FCA, and RAH. And because this is acting towards the joint, the horizontal component will be in this direction. So you have the horizontal component like this. So this one and the horizontal reaction at A are of same nature. Therefore, FFA should be in this direction. And therefore, we can say FFA is tensile in nature, and the sum of these two is equal to FFA. So FFA equal to RAH plus FCA cos theta, that is equal to 12 kilonewton tensile. Now you got both. We are moving on to the next joint here, which is joint C. Now you know the forces on this member here and this one. FCA is 5 and FFA is 12 kilonewton. FCA is 5. Let's say that 5, and FFA is 12, and FCA is compressive, so that is like this, and FFA is tensile, so it will be like this. Now you need to find FDC and FFC. For vertical equilibrium, you have two forces. The vertical component of FCA should equal the vertical component of FFC, and it should be opposite, so that there is a vertical equilibrium at joint C. So FCA sin theta should equal FFC sin theta, and because this is acting compressive, we know it should be tensile. So this is tensile, and FCA sin theta equal to FFC sin theta, or cancelling the sin thetas, you have FCA equal to FFC, so that should be 5, same 5 here, but the nature is different, it is tensile. Now the horizontal component of this force should equal FDC, the horizontal of FFC and FCA. So FCA cos theta plus or minus FFC cos theta plus or minus FDC should equal 0. And we can see these are opposite direction, but the horizontal component of both the forces are same nature, because FCA, because it is acting in this direction, you have the horizontal component. If you have a FCA like this, you will have the horizontal component in this direction, and for FFC, which is acting like this, you will have the horizontal component in this direction. So both these are acting towards the positive x-axis. Therefore, FDC should be in the opposite direction. And you have FDC equal to FCA cos theta plus FFC cos theta. So FDC equal to 5 into, we have already calculated the cos theta value here, and all the thetas are same. So cos theta is, it's given here 0.8. So you have, substituting the value of cos theta here, you have 5 into 0.8 plus 5 into 0.8. That is equal to 8 kilonewton, and it is compressive. Moving on to the next joint, which is the joint F. You have, you know the FDC is 8 kilonewton, FFC is 5 kilonewton. FDC is 8 and FFC is 5 tensile. FFC is 5 and that is tensile. So FDC is compressive. Actually, you don't need that while calculating this one. You actually need FFA, and FFA is 12 kilonewton tensile. It is 12 kilonewton tensile. So to balance F, you have the horizontal component and vertical component of FFC, horizontal and vertical component of FDF, the 3 kilonewton vertically downward, and the horizontal FFA and FGF. Now, for the vertical equilibrium, you have FFC vertically upward from the joint, so you have the vertical component of FFC acting upward and a vertical force downward. So 3 kilonewton minus FFC sine theta should equal FDF, because these are acting opposite, and that should, we are assuming FDF a direction, any direction, but here you can see FFC is 5 kilonewton and the vertical component is 5 sine theta, which is 5 into 0.6, and you have a vertical force here 3, so 3 minus 5 into 0.6, that is 3 minus 3, that is equal to 0. Therefore FDF is 0. Now for FGF, you have horizontal force FFA and the horizontal component of FFC, and you know the horizontal component of FFC is acting in this direction. So you have 12 plus FFC cos theta is equal to FGF, and therefore FGF should act in this direction, and therefore it is tensile. So 12 plus 5 cos theta, that is equal to 5 into 0.8 plus 12 equal to 16 kilonewton tensile. Now moving on to the next joint, which is D, you will need FED, FDF and FDC. FDC is 8 compressive, kilonewton compressive. FDF is 0, which is null there is no force, and you will need to find FED and FGD. Because there is no vertical component, you can say FGD also is 0, because you don't have a vertical force here. So the vertical component of FGD should be 0, and therefore FGD equal to 0. Therefore FDC should equal FED, and that should be in opposite direction. So you have FED equal to 8 kilonewton, and that is compressive. Moving on to the next joint, which is joint G, you will need FGD. We know that's 0 now. So FGD is 0. You have FGF there. FGF is, we will need to find FGF from joint G, and you have a 6 kilonewton force, FBG and FEG. So for vertical equilibrium, you should have FGD is already 0, so the vertical component of this force should equal 6 kilonewton. So FEG sine theta should equal 6 kilonewton. You can see the vertical component of FEG. If you resolve this, it will be like this. So in order to balance the 6 kilonewton, the vertical component should be in this direction, and therefore this force should be in this direction, and hence it is tensile. So FEG is tensile in nature, whatever be the magnitude. Now the sine component of FEG should be 6. Therefore FEG sine theta equal to 6, or FEG equal to 6 by sine theta, which is 6 by 0.6. That is equal to 10 kilonewton, and it is tensile nature. Now the horizontal component is in this direction, and that will be 10 into 0.8, which is FEG cos theta, and that should equal these two forces, or that should balance these two forces. So you have FEG cos theta is equal to 10 into 0.8. FEG cos theta equal to, this is 10, and that is 10 into 0.8, that is 8 kilonewton. So that's the horizontal component of this force. Now for the balance horizontal equilibrium of this joint, you should have the balance between FGF, FBG and the cos component of FEG. Now this is acting in positive x direction, and you don't know the direction of these two forces. Hang on, we have FGF, we have FGF. Yeah, FGF is 16 and tensile. Yeah, that is 16 and tensile. FGF is 16 and that is tensile. So this is opposite to 16, and we know this is 8, so you should have another 8 here, and it should be in this direction, because this is only 8 and you have a 16 here in the opposite direction, so it should be 8 and that should be tensile. So 8 plus 8 equal to 16. That gives the horizontal equilibrium of joint G. Moving on to the next joint, which is joint E here, you will need FED, FEG, FBE. So FED is 8 compressive, FEG is 10 tensile, that is 10 tensile, and you will need to find FBE. So for the vertical equilibrium, FEG sine theta should equal FBE sine theta, and that should be opposite direction. So the direction is compressive, and 10 sine theta equal to FB sine theta. So FB equal to FEG sine theta divided by sine theta, or you can cancel the sine thetas. Therefore FB equal to 10, and that is compressive. Now the cos component is like this. FED is 8. Yeah. Now if you want to check the horizontal equilibrium, you can double check with 1, 2, 3 and 4. Now the horizontal component of FEG will be like this. That is 10 cos theta, and this too is 10 cos theta. So that will be 10 cos theta is 8. So this is acting towards the negative x direction. This too is towards the negative direction. So 8 plus 8 is equal to, here you have 8 acting towards the positive x direction and another 8 acting towards the positive x direction. So 8 plus 8. So that balances the horizontal forces on the joint E. So after all this, the entire system is shown here, the complete forces on the system, and I just missed to mark one force direction here, which is the FBE, that is compressive. So 8 kilonewton, 8 kilonewton, 8 kilonewton, and 5, 5, 2 zeros, and 10, 10. RAV is 3, and RAH is 8, 6, RB is 6. That is 3 kilonewton. That is 6 kilonewton. RAH is equal to 8 kilonewton. If you have any confusions on how to calculate the moment or how to resolve a force, go through the videos shown here, in which I have discussed in detail how to calculate the moment and the resolution of forces.